Hello everyone, today let's take a look at another combinatorics question. It's going to be a derangements one, quantipose number 61. We need to find the number of derangements of the integers from 1 to 10, basically satisfying these two conditions down here for part A and part B. Both of these parts should be really easy to solve if you've been following the roadmap. Let's look at part A first. So here I've written out the 10 places to put the numbers 1 through 10, right? 1 should go here, 2 should go here, you know the drill. So in part A, we're basically saying that 1, 2, 3, 4, 5 need to go in all the places before this line in the first 5 places, right? And that necessarily means that 6, 7, 8, 9, 10 need to go in these places over here. So you can clearly see we've broken it down into two subproblems. First, let's calculate the number of derangements for 5 elements, right? 1, 2, 3, 4, and 5. We also did this in quantipose 55, but I'll just go over it again one more time. Basically, there's 5 factorial ways to permute these 5 elements here, and we want only the ones that do not have the number in the place that it's supposed to go. So let's just subtract off from our total the number of arrangements of these that leave any of these elements in the correct position. So this is just basic inclusion-exclusion again. Let's calculate our singular terms first. Let's say we fix 1 in place, and then the other 4 have 4 factorial ways to permute those. And then let's fix 2 in place, and the remaining elements, there's obviously 4 factorial ways to permute those. And then when I fix 3 in place, similar story, and same with 4 and 5. So I have 5 different ways of fixing an element, and for each of those, I have 4 factorial ways of permuting the other elements. But now I'm over subtracting the cases where 2 elements were fixed in place, right? So I need to add those back. So how many ways can I fix 2 elements? Well, I have 5, and I need to choose 2 of them, so it's going to be 5 choose 2. And then once I fix 2 elements in place, I have 3 factorial ways of permuting the remainder of them. Now I need to subtract off the cases where I have 3 fixed points. Again, this is just by inclusion-exclusion. So how many ways are there for me to fix 3 points? Well, 5 choose 3. When I do that, I have 2 factorial ways of permuting the remainder. Then I fix 4 elements, so 5 choose 4, and there's just going to be 1 factorial, which is 1 ways of permuting that. And then I just need to subtract off the final case where I fix every single element. We've already calculated this in QP55, but let's just do it again. I have 120 minus 120, and then I add 60 here, minus 20 plus 5 minus 1, and that's going to end up equaling 44. So there's 44 ways of deranging these first 5 over here, and there's also going to be 44 ways of deranging these 5, right? We just have 5 elements again, and these are the places that they should go. So for every single one of these derangements, I have another derangement over here. So let's multiply 44 by 44. And that's just going to equal 1936. So the answer for part A is just going to be 1936. So now let's just move on to part B down here. And this part's going to be even easier because 6, 7, 8, 9, and 10 need to be in the first 5 places, which necessarily means that 1, 2, 3, 4, 5 need to be in the last 5 places. So since the first 5 places have positions 1, 2, 3, 4, 5, obviously there's no possible permutation of these elements that would not be a derangement. Similarly, these are going to be positions 6, 7, 8, 9, 10, so there's no way that 1, 2, 3, 4, 5 can be permuted such that it's also not a derangement. So again, it's 2 subproblems. Let's do this one first. Every permutation is a derangement, so how many permutations are there of 5 elements? Well, 5 factorial. In this subproblem, there's also 5 factorial derangements for the exact same reason. So for every one of these, we can match it up with 1 from over here. So let's just take 5 factorial and multiply it by 5 factorial. That's just going to be 120 squared. And this is just going to be equal to 144, and then we're going to tack on 2 zeros. So 14,400 is the answer for part B. So again, this should be super simple if you've done the previous derangement problems.